And we, Nyro Research India, are the sole authorized reseller for the AMS software. And these are the modules under AMS Cosmos Suite. And kind attention to everyone. So workshop slides and links will be shared via email to all the attendees after the session. Agenda is shared with all the registrants, and software download links will be shared today post session. And certificates will be distributed to everyone after the after all the 7 workshops, and after the feedback forms are filled. And the feedback forms will be activated starting from October 10th. So if you have any queries related to software, you're always free to send an email to support@nyroindia.org, and you may call us at this number. And these are the 6 sessions with 1 day Q&A session. Yeah. So today there will be session on introduction to AMS software and improving battery performance using ReactFF, and that will be taken by Dr. Ole. So he's from SCM Netherlands. And I would like to introduce our speaker, Dr. Ole, to everyone. Dr. Ole received PhD in 2014 with Professor Artke in Kiel. So Ole has been working in improving usability, graphical interface, and scripting, and implementing new functionalities in ReactFF software. Ole currently focusing on helping existing and potential customer for their advanced scientific applications, and he also works on the marketing materials and represents the SCM at conferences and workshops. Over to you, Dr. Ole.
Okay, thank you very much for the kind introduction. And let me share my screen. So now you should be able to see my screen, I hope. If not, please let me know. Okay, so yeah, as mentioned in the title, what I had planned for today is actually a bit less of a hands-on session and more of of a small overview, I shall say. So I would like to say a few words about who we are, where we come from, and what we do over here in Amsterdam in the Netherlands. And then in a second part of the talk, I would like to zoom in into some specific functionality of the Amsterdam modeling suite, that is ReactFF, the reactive force field ReactFF, and highlight 2 recent/successful battery applications of this particular module from the past. One that is already a bit, seasoned and proven, and one that is pretty much cutting edge. Throughout this whole presentation, I have put links into my slides. So once you receive the slides, you can just click on the links, and these links will lead you to tutorials, very detailed step-by-step tutorials, and some also YouTube videos. So we have made part of this talk were made into YouTube videos where I explain everything in much detail with some nice animations and supplementary materials and so on and so forth. So since this is not really hands-on, I would encourage you, if you see something of interest for you, to just follow the links in the slides and give it a try. And if you do so before the Q&A session, then you will even be able to ask some questions to us in that Q&A session. Okay, so let's begin at the start. And the start was taking place in the 70s already. So that's our roots. The roots go back to 1973, around 1973. That is when Professor Evert Jan Barents started taking density functional theory from the physicists community and applying it to chemical problems, basically to understand inorganic chemistry problems with the help of computational modeling. So in that aspect, he was really an early adopter. So this was as early as it gets, as you can also see here on the right in these small sketches shown here. These are basically articles and patents with the keyword density functional theory. So 1970 is not even on those timelines here to be seen. So that was really very, very early. And with this pioneering spirit, this was successful. So that started growing and that started raising interest also in industry. And not too long after, the Barents Group at the FÜ started supporting industry customers, Shell, Akzo, Mitsui. Those work was mostly focused on catalysis applications, as far as I know. This was before my time at SCM. But commercial interest grew and the number of users grew. So eventually, the company SCM was founded in the 90s. So 1995, SCM, Software for Chemistry and Materials, was founded. And the purpose of SCM up to this day is to develop, debug, port, optimize, and support the Amsterdam modeling suite. So in the beginning it was ADF, but soon after there were coming more software codes, and a whole package was formed. And this package, which we will have a look at in a second, this package is what we call the Amsterdam modeling suite, so AMS in short. And up to this day, we start expanding, growing the Amsterdam modeling suite. So the latest thing that we have been working on is extending into the multi-scale modeling region. Also on that, we will have a bit more details in the next slide. At this moment in Amsterdam, we are 29 people. 21 of those are senior PhDs in the relevant scientific fields, mostly chemistry, I think exclusively chemistry and physics, and 2 EU fellows, European project fellows. We collaborate with many academic collaborators all over the world, many EU networks, funding, and so on and so forth, and are located in Amsterdam. The Amsterdam Modeling Suite, this is a bit of a sketch picture here. On the left, you can see we have some sort of scale. Say we at the bottom have the atomistic scale. And this is basically the seed from which all this was developed and this was growing. This is the ADF program. So this is a molecular DFT code. With this code, you can calculate very precise quantum mechanical properties. I'm talking spectroscopy, for example, inherent quantum mechanical properties for small and medium-sized atomistic models. So there we treat really explicit electrons, and we have to solve the equations numerically. And there is just a computational limit to these sort of approaches. So these where you cannot run, where you cannot finish such a calculation anymore even on a compute cluster. So entering the nano realm, we have extended the Amsterdam modeling suite with some more approximate methods, and these approximate methods are just computationally cheaper, so they are more efficient. That comes at the expense of those methods being also a bit less precise, a little bit less accurate. So to name but a few examples, we have some type binding codes. So that would be Stefan Grimme's GFN XDB, for example, that allows you to still run quantum mechanical calculations, but these are parameterized models, so not everything has to be evaluated in an ab initio kind of way. And you can calculate much bigger systems with those models. And then as we go up the scale here, we get more and more approximate. Maybe I should just mention some of the most recent add-ons would be machine learning potentials here on this upper field in the force fields realm. This is a new thing. I will not cover that very much in this talk, but in the Outlook, I will show or highlight briefly an application of the new machine learning potentials. So these are, interatomic potentials. These are potentials that are powered by a machine learning approach. So this is something new, but this is new and powerful, and this has been incorporated already quite successfully in some of our new workflows. Then, of course, we have here the reactive force field ReXFF. We'll see a bit later what that is all about, and then we'll also see some applications that are linked to batteries of this ReXFF force field. On the upper scale, we have some kinetics code. So we have a kinetic Monte Carlo code PyZacros, for example, and then up into fluid thermodynamics. And there are ongoing efforts to even extend these tools into reactor modeling. So we fluid dynamics reactor modeling kind of scale. This is also handled and taken on in collaboration projects with industry at the very moment. So if you're interested in such things, I suggest having a look at our website. There you can see all the latest collaborations and projects ongoing. Parts of the Amsterdam modeling suite that is not computational modules are also PES exploration tools. So for example, one of such tools could be molecular dynamics. It's basically exploring a potential energy surface, and there's many ways how you could do this. You could solve Newton's equation of motion that gets you then into the molecular dynamics area, or you can run a Monte Carlo approach. There are different Monte Carlo and acceleration techniques included in the Amsterdam modeling suite, and all these sort of drivers are abstracted in a way that you can use them with all the compute engines. So if you know how to run molecular dynamics with ReXFF, then you can apply the exact same settings and setup also to, say, GFN XTB, given it's computationally feasible, of course, but the setup panel is going to be the same. That is because that molecular dynamics driver is abstracted from the actual compute engine. All that this molecular dynamics driver needs, gradients and molecular structures, coordinates, is provided by the engines and is completely independent. The whole thing comes with the graphical user interface. So you find all sorts of tooltips. You can manipulate your input files, your structures. You can visualize your results. We have a remote job management, so you can send and receive jobs to your compute node from your local machine, all these kind of things you can do. This is usually, this is very convenient when it comes to creating workflows, to refine workflows. But then if you want to, say, power use AMS, if you want to automatize established workflows, if you want to do high throughput calculations, say you're from industry and you want to screen for example, for polymers or redox potentials, or something like this. You know, you have a lot of candidates and you want a high throughput calculation to screen for some properties. Then under the hood, we are shipping a full scientific Python stack. And the Python stack is linked to all our compute codes via our library called Plums. So that's an in-house developed Python library. So it's a Python layer for automatic molecular simulation. And with this, you can control everything that you see in the graphical user interface very easily and conveniently also from Python. And you can imagine once you get into that stage, it's very easy to just run high throughput calculations, to customize your workflows very precisely, to automate the extraction of results, and so on and so forth. And there's no need to install anything. So that's also true when you get your trial license and you are trying the Amsterdam modeling suite, the whole suite. Wherever there's AMS, there's Python. The Python layer is always there. If you have AMS installed, there is a Python layer there. So you can access the AMS Python via a command line that comes with your AMS installation. It's accessible also from the graphical user interface. Just to give you an idea how we are, who we are, this is our current team. You can see on the top left, Professor Evert Jan Barens, and we are very, very fortunate that he's around. He's doing well, and he's emeritus by now, but he is our scientific advisor and founder, of course. The offices are still located on campus at the Free University. This is just a picture of the front of the building. We are actually located in an office building behind this one. And this is an aerial view, top view of the city of Amsterdam in the Netherlands. Very nice, very old historic city. We are just not in this picture, just to the south a bit is where we are located. Now, onto the first, onto the compute engine ReXFF. Now, the ReXFF force field has been around for quite a while now, so there's a chance that some of you are already familiar with the concept. But for those who are not, let me just very briefly sketch what this is all about. Now, you might have heard of classical molecular dynamics force fields, classic bio force fields. For example, AMBER is such a force field, or GROMACS, that people use in molecular dynamics simulations for big proteins, big biosystems usually. And these force fields, they are replacing this iterative solution of basically the Schrödinger equation with analytical, physically meaningful formulas, such interatomic potentials that will just give you an energy or a gradient depending on a given molecular coordinates, given coordinates of the atoms. And of course, these are highly parameterized models. So for every sort of bond, we basically need to provide parameters. And in these classical models, what you typically do is you have a harmonic potential. And if you just take a look at the top left here, you see a sketch of what that means. What that means is that there is no asymptote. So it doesn't matter how far apart you stretch these two atoms in this cartoon example here, you will never be able to dissociate the bond, because this parabola, this harmonic potential, just extends into infinity. The further you stretch apart, the higher the force will be that will lead you back to equilibrium, but it will never find any sort of asymptote or dissociation. It's just not possible. It's not in this model. That means that no matter how hard you stretch a bond, how far you stretch a bond, a triple bond, if you once at the start of your simulation assign a bond to two atoms, a triple bond, it will always be a triple bond, because there's no reassessment of this initial assignment in those force fields. So everything that was a triple bond will forever be a triple bond. And it doesn't matter what conditions your simulations have. Excuse me, I think somebody in the audience has their microphone on. If you don't mind, can you please turn off your microphone? Thank you. Okay, so what I was saying is, since there's no reassessment of the initial assignments of bonds in these force fields, a triple bond will forever be a triple bond, and that is true even if it was in the center of the sun. It's just not in the model that the bonds can dissociate, and this is something that is different with ReXFF. So ReXFF is a reactive force field. The name kind of already gives it away a bit. So without going into too much details, the central difference between these force fields is that now we have non-harmonic potentials between the atoms, and these potentials are based on bond orders. And the bond orders on their turn, they are based on interatomic distances. So based on the distance between two atoms or several atoms, a bond order is calculated, and this bond order is used in the potential energy expressions. And this is re-evaluated continuously during the dynamics, during the calculation, evaluation of whatever sort of calculation it is you're doing. Could also be Monte Carlo, of course. And the most immediate and most important consequence of this is, of course, that it's possible to dissociate, to break a bond. And this is the difference between classical force fields and ReXFF. Now, behind the scenes, this is a lot more complicated. So this, this flexibility, this capability of ReXFF comes at the price of a lot of added parameters. And parameterization of ReXFF force fields is not a simple task. It has very, very many parameters, and they are very unintuitive parameters. But it is possible. Those models are usually trained against ab initio data, so for example, ADF calculations. And if you are interested in such a problem or in training ReXFF force fields, then we have also a code in the Amsterdam modeling suite called params that deals specifically with that. But for the coming few slides, we will just use parameters from our parameters library, ReXFF parameters library. And we continuously update this library. So when we are seeing that there are new published parameters, we are adding them. If you come across a set of parameters in literature that is not yet part of the Amsterdam modeling suite, you can always reach out to us. And as long as the parameters are actually published, so if they're found in the electronic supplementary information, for example, then you can just tell us and we will add them to the force field library that we ship with AMS. So in this ReXFF method now, this force field we can apply to all sorts of materials modeling problems, but since our objective here is battery modeling, we'll have a look at two applications on batteries modeling of this reactive force field ReXFF. And the first one is the calculation of a voltage profile with the help of a grand canonical Monte Carlo simulation. So this is basically simulation of the discharge process that takes place in a lithium-sulfur battery setup. So on the left here, we have a sulfur cathode, which is nothing else than just a sulfur crystal structure that you can take from a crystallography database. You can load it into ARMS. And what we want to simulate is the increasing intercalation of lithium into this sulfur structure, as sketched here on the top. And at the stage where the intercalation is complete, the battery would be discharged. And the way we can do this is by running a Monte Carlo simulation. And the Monte Carlo simulation we want to run, so we're using this Monte Carlo simulation to generate a grand canonical ensemble. And the ensemble we want to generate is the one constant number of sulfur atoms, constant pressure, constant temperature, and constant chemical potential of the lithium atoms. So in the lithium atoms chemical potential we can calculate by basically optimizing the structure of bulk lithium and then taking the energy of that and the energy we need to remove one lithium atom from a bulk lithium structure. That is what we take as the chemical potential of lithium in this simulation. And the Monte Carlo simulation does nothing else than generates trial moves. So these trial moves I have sketched below here. So obviously one trial move would be to just insert a lithium ion at a random position inside this sulfur structure. The next Monte Carlo move would be to move a lithium ion that we have inserted earlier. But we can also remove a lithium ion and we can shrink or expand the unit cell of the structure. So we'll be able to simulate the expansion of this whole system, which is actually an experiment. Excuse me, someone has the microphone on. Thank you. So we can also simulate the expansion of this unit cell, of this structure, which is actually one of the challenges in the experimental design of such batteries, is that upon intercalation of lithium ions, these cathodes are swelling up. So this is also caught by this simulation here. Yeah, and then if the energy is lower, after our Monte Carlo move, we accept. And if the energy is higher than it was before, we accept with a certain possibility, and the possibility gets smaller the higher the energy is compared to the initial structure, which is like, yeah, classic Monte Carlo. I won't go into too much more details here because you can find all the information in the online tutorial. Like I said, there are links in these slides, and the slides will also be shared with you. And we have a very detailed walkthrough on our YouTube channel as well. That is also a link here at the bottom, in which you will find some more information on the motivation of this simulation, say on lithium sulfur batteries, on the functioning of lithium sulfur batteries, on why this is interesting to run such a simulation, what you can get out of it, and a complete walkthrough of the actual calculation itself. Okay, so for now, what we are going to do is we can have a look at one of the results of this simulation. And this is a small movie of this discharge process. This is an animation taken from the video here. So you can see as the Monte Carlo simulation proceeds, the fraction of lithium ions inside the system increases compared to the sulfur atoms. Their number is kept constant. The number of lithium atoms is subject to the Monte Carlo simulation. The voltage is calculated from the number of from the energies and the number of intercalated lithium ions. And the discharging battery here is just an illustration, a cartoon illustration. So here we can see what the results look like of this simulation. So you can see that you can actually simulate quite a nice voltage profile that combines quite nicely, that compares quite nicely to experiment. And you also catch the volume change that happens during lithiation, which is, like I said, one of the main experimental challenges in these battery materials. And once you have established such a workflow, you can, of course, apply this to other cathode materials as well, given that you have the correct, that you have suitable, let me put it like this, suitable force field parameters available. Okay, so on to the next topic. And the next topic is a topic that is a bit, say, less established than the topic that I've shown earlier. So the discharge voltage profiles, they have been already out there for a while and have proven their use, say. And this is a pretty cutting edge application here. So the ReXFF force field has recently been expanded. And this has been called eReXFF. And this allows for the pseudo-classical treatment of explicit electrons. So in a nutshell, what it means is that the ReXFF force field has been extended to include parameters for explicit electrons. So you have a simulation in which you will have explicit electron particles flying around. So there are also whole particles available, but in the examples I will show now, we will only deal with explicit electrons. As you can imagine, there is quite interesting theoretical work behind all this. Again, I won't go into much detail, but if you are interested in such things, then I suggest you follow the links here on the slides and take a look at the according publications. And from practical considerations, what happens is that you basically change the way you represent the atoms in your system. So before, in the previous simulation, we had neutral lithium atoms and neutral sulfur atoms. You can have polarization effects in these reXFF calculations, but you cannot really study redox reactions, at least not with the standard force fields. But with this eReXFF force field, you actually can. Now, the lithium atoms are actually lithium ions. So lithium carries a charge, 1+, and a neutral lithium atom is represented as a pair of an electron and a lithium cation. And the same is true for the carbon atoms in the simulation. So we have a carbo ion and an electron, and a neutral carbon atom is formed by the pair of these two. And this is the central difference in the setup of this calculation, I would say. And since you are treating the electrons explicitly, you are also able to view transfer of electrons between different components in this system. And the system that was studied here, and on the right side, the battery relevant system, that is basically, graphene sheets. So graphitic anodes of lithium-ion batteries are the simulation target. And what you can observe in these simulations is electron conduction. So you can see the electrons diffusing or moving around on these graphene sheets in plane. And if you extend the unit cell to more graphene sheets, you can also see out-of-plane movements. You can see how this depends on the temperature of the simulation. You can see how this depends on, or how this is impacted by imperfections in the material. So if you have defects in the graphene sheets, if you have connections between the graphene sheets, how does this affect conductivity of the electrons? All these kind of things you will be able to see in these eReXFF simulations. You can also see the beginning, the onset, say, of lithium metal plating, which is basically when a negative charge from a graphene sheet is transferred to a lithium cation and forms metallic lithium, or just neutral lithium atoms, and these lithium atoms then start bonding to each other, forming these, or beginning to form this metal plating process that is of relevance for such battery materials. We do have a tutorial online. We have documentation online on this. This workflow here, and I will show a trajectory in a second, that is also accessible on our website. Again, everything is linked. There is a YouTube video also if you're interested in this eReXFF applications, but that is not immediately, this is not so close to battery modeling immediately. This is electron transfer through an aliphatic carbon chain, but still, I think informative and illustrative of the eReXFF concepts. I think we have another open microphone somewhere. If you don't mind checking, please.
Hey, Sol, I'm just checking on it.
Okay. And this eReXFF trajectory is something that we can now have a look at in this animation here. So this is now one of many different eReaxFF trajectories that you can run with this force field, and that has been run. This is just one of the examples that we have on our website. This is a negatively charged graphene sheet and a lithium cation. And what you will see now is that an electron is transferred, and that happens very fast actually, to this, there you go, to the lithium ion. So this is now a neutral lithium atom. It looks like this in the eReaxFF simulation. So you see that this electron cation pair is formed, and as we saw here on the left, this now in this simulation is a neutral lithium atom. And this is the first stage. So this lithium ion capturing this electron of this negatively charged graphene sheet, this is the first stage of this metal plating process. So if we add more lithium atoms, lithium cations to the simulation, more electrons, they will start to meet on the surface, and they will start forming metallic bonds, and then this metal plating takes place. But there have been many more of these simulations run. Let's have a look at it one more time. You see all these green spheres, they are representing explicit electrons. And in terms of battery modeling, this is a very exciting new feature. As you can imagine, if you are able to study large systems for long times, because this is a very efficient computational code with explicit electrons in the system, then this is a large step towards modeling the actual functioning of batteries and battery materials. Many of these processes I have outlined here in the bottom, but there's many more coming to mind, like electrolyte degradation, for example, dendrite formation, you name it. There's really, as long as you have suitable parameters for the system you want to study, then there's a lot of things possible, and I expect that there will also be a lot of exciting publications coming out of this eReaxFF ansatz fairly soon. Okay. Now that actually brings me to the end of my presentation. I just want to outline some more interesting applications from batteries modeling that are not or partially ReaxFF. The first one being that we also have Apple and P polarizable force fields. So this is not a reactive force field, but this is a polarizable force field. And what makes this force field special is that it was specifically made for electrolytes and ionic liquids, so that yields very nice results when you want to study electrolytes. Worth a look if you're interested in that. There's also a nice workflow with ADF and COSMOS, that's our thermodynamics code, to model accurate redox potentials. Then this is a cutting-edge application. So this is a very recent application, actually, so I don't think that there is a tutorial for this yet, but there will be very soon, of the machine learning potential called M3G net. So this is also, it is like a force field, but it is not using force field parameters, but a machine learning backend. And what you can see here is the prediction of intercalation potentials, M3G net, so the fast machine learning potential compared to a slow but much more accurate, to a slow but accurate DFT model or experimental data. And you can see how well the machine learning potential compares here. And the exciting bit about this is that the machine learning potential is orders of magnitude faster. So you can just, on your laptop, you can just run these calculations in, I think I ran it in a couple of minutes, basically. So you get these results very fast, very accurate, as opposed to running this for many hours, if not days, depending on system size. As one example of say trajectory results and trajectory analysis, I put lithium-ion diffusion coefficients here at the bottom. We have a lot of functionality for automatic trajectory analysis. So that is to extract results from your trajectories. Diffusion coefficients are just one example. I think probably most relevant to battery modeling. So information about how our charge carriers, our lithium ions, are diffusing in the system is of course very relevant, very interesting. In the tutorial that is linked behind this link, you will find that we study the diffusion inside this sulfur cathode that we have used for the voltage profile Grand Canonical Monte Carlo simulation I showed you earlier. But there are many other ways that you can analyze your trajectories, and there are also ways to analyze your trajectories that are specific to reactive molecular dynamics, because if you can form and break bonds, then you obviously have much more information in a trajectory than you would if you wouldn't allow for bond breaking and bond formation. So that also requires some thought or some more particular methods of analyzing these trajectories if there's more things happening on that side. All of that you will find in the graphical user interface and also in the Python layer if you want to automatize these things. And finally, of those things I didn't show here now, there's more. So this is not all, this is just a selection I made because I thought this might be most interesting for you if you're into batteries modeling. If you go to scm.com/batteries, you will find a list of tutorials and highlights and papers, videos about all things batteries. And it's a good place to start your journey, take it from there and dive in and see how far you can get with batteries modeling. And on this, I would like to end my talk and thank you for your kind attention. And I don't know if we want to do a bit of questions now, or if we want to save up the questions for when you actually had the chance to run some calculations yourself.
So do you have any questions, participants?
Ma'am, actually, I have a doubt. Am I audible? Hello?
Yeah, yes. I hear you.
Yes. Actually, whether you have done for LFP or LCO type of material, like LFP will be a flat discharge curve, no?
Sorry?
So whether that modeling was done, lithium iron phosphate will be a flat discharge curve, no? So whether for that, whether we have done the modeling, because YouTube also I saw this material only, Li2S. Lithium, this lithium iron phosphate or maybe LTO as an anode material, whether for that we have done a modeling for that and obtained the curve, discharge curve.
So let me see if I get your question right. Sorry for not understanding if I didn't. So the question is that you are, do I understand correctly that you are interested in different materials and that you have run your own, that you have modeling results on a different material, phosphate-based material, is that right?
Yes, but not using this software. Actually, I used a different software. So because flat discharge curve, it is a little bit, means it's not easy to model. Because iron phosphate will have a flat discharge curve with lithium or maybe with some anode material.
Okay, so whether that discharge curve, you refer to the voltage discharge curve, right?
Correct.
Okay, yeah. Well, there's more than one way to do it, and I think in the end you could apply this this workflow to other systems as well. the workflow is fairly general. Also, this is I should add maybe that this is a fairly approximate way of generating the grand canonical ensemble. It's possible to also do a much more thorough way in which you actually basically equilibrate on the how do you say, on the separate ratios, lithium sulfur ratios. If you really thoroughly equilibrate on those steps, you can get a much more exact result too. So this is sort of a bit more approximate way of generating the grand canonical ensemble, but still, you know, the result is fairly okay. In the end, you can get it more accurate if you invest more time in it. You can try different systems. You can try also different engines. So I know that this has also been run with tight binding codes, for example. So the more computational time you are willing to invest, the more accurate you get these results. This is just, I think in general, this is true. And in the end, if you're even willing to take existing parameters and reparameterize a force field or tight binding code, you can also reparameterize tight binding codes with the AMS software, with params. Then you can get an even higher accuracy. So, you know, if you have calculations, if you have run calculations with other codes, if you have reference data, if you have good ab initio or experimental reference data, I think reparameterizing is also always an attractive option. And in the end, I think in most commercial applications or in industry context, I think it's good to have a huge toolbox. So, you know, there's different ways to do it, and the more flexibility you have, the more tools you know how to use. In the end, you look which one is the best for the job. So that's, I think, when it comes, that was just a bit of my 2 cents on exploring different options, going to different systems. I hope that answers. It's not really an answer, but it's more a comment to your comment. I hope that's okay.
Actually, Ole, there is a questions in Q&A tab. Can I just read for you?
Yeah, sure.
Okay. Dr. Sharma has asked, so he wants to know about modeling of interface on solid electrode and electrolyte.
Yeah, you can also do that. And yeah, I mean, in general, if you have good parameters for this, there is ways how to do that. I mean, depends what exactly which process you want to model there. But there's publications that are doing this, and yeah, they're asking different questions and study different things. So I think yeah, as I said, I think it depends what exactly you would like to know.
Mr. Sharma, do you have any other questions related to this?
It's okay for now.
Sure, sir. Okay, Ole, there is a second question. So could you please show a demo on the software and GUI?
Yeah, I have not prepared a demo now, but there will be in the coming sessions. There will be hands-on. So this is basically what I was referring to earlier. We don't really have a hands-on demo now, or I don't have, but you can. Let me just to give you an idea how that looks. There will be hands-on demoing. There will be hands-on demoing in the next sessions. Sorry, now we have to sit through this this quick commercial, but I just jumped into the into our YouTube channel now. to give you an idea how these YouTube tutorials look like. So you see, there's first sorry. There we go. There's first some general introduction. The Grand Canonical Ensemble, the system, the Monte Carlo. This is what the graphical user interface looks like. I hope you can see this now. Here I'm just importing now this cipher structure. For the this is a video showing how to calculate this voltage discharge profiles. You can choose different compute engines here on the left. You have control panels. You can see the task is maybe I should do it like this. So you can see that that the user interface lets you set all these things. Here I'm choosing now which force field parameter I want to use for the reactive molecular dynamics. This is easy for me to choose now because this is a reproduction of a paper that came out. So I just use the same force field that they use, but there's also tools. There's also video content on how to choose parameters. We start off with the geometry optimization. I want to optimize the lattice. Then you just save the calculation, and then you will see that while the calculation is running, this is all local now on a Windows machine. While the calculation is running, you will see what the status of the calculation is. You can follow the progress, see the structure changing. And all these things, as I said, you also can automatize them. So you see, this was just a geometry optimization. The geometry was already good, so it's fairly well converged. And once it's done, it asks you if you want to update your structure, and so on and so forth. Let's see. This is then how I generate bulk lithium. So there's tools for that too. Then there's another geometry optimization, and so on and so forth. The dynamics, once the dynamics are starting, this is the setup of the Grand Canonical Monte Carlo simulation. You see here mu-pt, constant chemical potential, constant pressure, constant temperature ensemble, handful of Monte Carlo settings. We explain all those in much detail in the actual tutorials. And this is the process of the simulation. So it starts off slow. It adds one lithium atom. It tries around a few things. Some Monte Carlo moves get rejected, others get accepted, just how it is with Monte Carlo simulations. And then after some time, I think this typically runs for an hour or so. You start seeing this intercalation. So this hope this gives you an idea what this looks like. And throughout the slides, you find these links to this tutorials and YouTube videos all over the place. So this is what this tutorials looks like. This image you saw in my slides also, and it really goes step by step. It says here you find the structure, download, import. This is how you calculate the chemical potential for lithium, and every step is explained. So if you just follow along, or even some troubleshoot here, if you just follow along, you'll be able to run this calculation yourself on your laptop or desktop computer. So you don't even need any serious computing hardware for this. Does that give you an idea what it looks like? As I said, my colleague Franco, I know for sure he will also do some more hands-on demonstration with the actual software.
Yeah, okay, thank you, Ole. So there's one more question. How can I add keywords in SCM ADF?
You can add keywords. Yeah, I can show. Let's see. Now I'm still I'm opening it up anyways. Okay, so I assume that you cannot, that there's a certain keyword that you want to add, that you found in the manual, that you are not finding in the graphical user interface for yeah, whatever reason. Maybe it's a bit hidden, or it's in expert settings or so. So this is the input, and everything that you set up here will of course find its way into the input file. The input file has the extension .run, but you can click everything here that you select and click, of course, that's the obvious way, but you can also go to details, run script, and there you will find the run script that is then fed to the actual compute code when the calculation starts. And this you can just edit now if you want. You can also pass parameters that you want to pass to before the script gets executed here. But this is how to add these. If you find something in the manual and you don't know where to find it in the graphical user interface, you would put it here. When working with the graphical user interface, be aware that you can, when you hover your mouse over input fields, you will get a description, a tooltip. So I think this is probably a really good tip if you start now when you install the software for your own trial. If you're not sure what this means here, just hover your mouse and read the tooltip. And there are tooltips for every input you will find in the graphical user interface.
Yeah, Ole. And in the chat box, actually, I guess there is a concern from Dr. Soumya Ranjan Dash. Do you have any comments on that in the chat box? Can
in
you
the
just
chat box?
Yes, there's a concern from Dr. Soumya Ranjan.
I will let me check because I don't. Where is it?
Yes, the modeling of
explicit electrons was really tough. This one?
Yes, you're right.
Yeah. That I can imagine. This is not an easy. This is not an easy task for sure. I mean, there are other models, right? That are treating pseudo-classical electrons. I think there was also EFF, Drude models, and so on. That were there before eReaxFF. But yeah, this has been also quite a long time in development. And this is a really challenging ansatz. So I understand that why it takes 8+ months to model this, but it seems like you succeeded. So congratulations on that. It's a challenge, and we have also been working a lot on eReaxFF, but now I think we entered a stage where this is really where this is taking off, say. So this video I showed you that is a really nice simulation, and my colleague Nicola Onofrio actually put this example together, and it just worked flawlessly for me. I tried it and it just worked. So hopefully we are off to a bright future. But there's always a challenge in it, I guess. It's just not an easy way to simulate these explicit pseudo-classical electrons.
Yeah, Ole, there is one more question from Dr. Soumya in the chat box.
Yeah, I will jump down. Oh, they failed. Okay, yeah, too bad. Yeah, well, the trial is fully functional. Sorry, just one more thing about this eReaxFF. So yeah, just give it a try and then follow the links in the publications. See how far you can get. Maybe it works for you with eReaxFF. So who knows? Fingers crossed. So how to build a graphene nanoribbon with 5 rings? Yeah, I am not sure how to build that myself in the graphical user interface, but I can look that up. But to be honest, I'm not building such things very often. So usually what I do is I'm importing crystal structures. I guess that is something that you cannot do because you are explicitly asking about building it. Otherwise, that would be my advice. Try to find a structure to import. But yeah, there is. I think we have a couple of videos. So say like long story short, and I cannot from scratch. I can also not just build this structure. So I would need to sit down and think about it. But we do have a couple of videos on advanced manipulation of structures and structure generation on our YouTube channel. So I think that would be a good place to start. Okay, another question. Compared to Gaussian, ADF is more time consuming. Well, I'm not sure about that, but how to speed up the calculations? Well, it depends a bit what calculations you're running, I'd say, because there are some calculations that are just not possible with Gaussian, I think. Yeah, it's conceptually different. It's a bit of a different ansatz. As you know, we're using different basis functions. So we're using Slater type orbitals as opposed to Gaussian functions. But there are lots of ways how you can speed up your calculations and how you can become more frequency calculation. Oh yeah, there's actually there are quite nice applications how to speed up frequency calculations. So you're interested in the spectrum, or are you interested in just confirming transition states? Because if you want to confirm stationary points on the potential energy surface, you don't need to run a full frequency calculation. You can just run path point characterization is what it's called. There's also videos on our YouTube. Spectrum, okay. Yeah, well, there's different ways how to do it. There's different ways, different more approximate. There's a lot of ways how to do it, but one way would be to refine the spectrum. So there is functionality where you can calculate an approximate spectrum with a fast computational method, and then you can say, I want this portion of the spectrum. I want this as accurate as possible. And then you can afford to run a very, very expensive computational model and to refine the spectrum. So that could be something for you to look into. There's many other strategies as well, but this is like one of the things that pops into my mind now. Let me see, just real quick. If I can point you in the right direction. There's also a lot of information in our manual on frequency calculations. So this is our YouTube channel, and we have playlists, tip of the week. Here are some tip of the weeks that I've compiled in the past, different topics. Yeah. So I suggest taking a look at this as a first start. If this doesn't do the trick for you, then you can always also look into the manual, and there's a lot more strategies listed there. But this is something that when I heard about it, I thought was quite cool, and that works really nicely, and that saves a lot of time. Okay, one more. Lithiation voltage, constant volume changes of the cell. Shows constant volume changes of the cell. I'm not sure I understand. So let me. So I'll read the story for the question. In the lithium battery tutorial slide, the lithiation voltage plot shows constant. My email is on the first of on the slide. Otherwise, you can also reach out to Nyro. Then we can establish contact. But it's also on the slides, on the first slide. ReFFX has predicted the gradual change in volume and not exactly same as experiment. Do you think still? You mean the final volume is not the same as in the model? Yeah, I mean you could probably run this for longer. I'm not sure. It depends on many different settings. I'm also not sure where this experimental volume change comes from. You could probably, if you really look into this, you could probably get it more accurate. But I think the goal in this was more or less to get it in the right ballpark figure. So I think you could probably get a better estimate of the volume change if one would look into this. I think it was not the primary objective of this paper to model that. It's just that it's nice that it's also caught to some extent.
Yeah, if anyone have any questions, you may unmute yourself and ask. Dr. Ole, looks like there's no questions. You may stop sharing your screen. So I will just share my screen.
Okay.
For thanking, yeah. Once again, thank you everyone. And tomorrow there will be session at 3 p.m. the same time. So we'll be focusing on two photon absorption using AMS by Dr. Franco. And if anyone have any queries, you can send an email at support@nyroindia.org, or you may call at this number. And today's session slides will be sharing as soon as at the earliest. And by today evening, I'll be sharing the software download links to everyone. And on September 27th, 28th, and October 2nd, 3rd, and 4th, the session timing will be at 5 o'clock. Dr. Ole, thank you so much for your time.
Yeah,
And
thank
it was
you.
a
You're
great
welcome.
session. And if anyone have any technical queries, I'll be dropping an email to you.
Yep.
Sure, we shall wind up the session for today. Thank you, everyone.
Thank you. Bye.
You too. Take care. Bye.